I also thank you for all those who have joined this session. And I have just started the session. I think it started recording. Yeah, we can officially start the today's session now.
Okay, so Vandana ma'am, whenever you feel you can start.
Am I the host now?
Yeah,
Co-host
I
now?
have made you a co-host, and you can share the screen if you have some slide show or to present your screen, and then yeah, you can start.
Okay. Okay, I'm not able to get this option of the Chrome in this, Windows in this. I'm getting an option only of the entire screen.
Yes, you have to, I think, show your entire screen. That's fine.
Okay, okay. Is my screen visible now?
Yes, visible.
Yes.
Okay, okay.
Okay, the screen is visible now. The presentation is visible.
So thank you so much for this opportunity, and to Dr. Sugam as well as to Indian Society of Atomic and Molecular Physics, ISAMP. And today this talk is going to be on, I think it is an overview again of qubits and quantum gates, which has already been covered, but also on the IBM Composer and using Qiskit. And so I will be just beginning forward. Is it hello?
Yes,
Okay.
we can see your next
So
slide.
okay, thank you so much. So, according to Coleman, quantum technologies are difficult to understand, but that will not stop the disruption this kind of emerging technologies will bring in the next few years. And we are seeing a phenomenal changes in this field, which is quite challenging as well as unprecedented. And according to Albert Einstein, which says that I have no special talent, but I am only passionately curious. So these words are again going to motivate all of us. Technologies are diversifying, and in this regard, understanding of qubits and implementation of quantum gates is a fundamental requirement, and it is the backbone of all applications which we see in gate-based quantum computing. And in this case, there is a lot more importance to mathematical framework and also the underlying mathematics and many other interdisciplinary field, which gives again a motivation for all of us to understand different game quantum composer and a variety in the Qiskit will also be provided. Interdisciplinary field which derives its motivation from mathematics, underlying mathematics in the form of linear algebra or matrices, and many other applications are there. Electronics, nanoscience and nanotechnology when we are talking about the fabrication of different aspects of it and manufacturing, and also enhancing the efficiency of it. Computer science also, we will see that all these applications are also derive motivation from or employ computer science, physics, materials, physics, because these devices also work in a field, and that is why which make this field very exciting and very challenging because of the interdependency of one field on the other. And when we are expert in one field, it is also required we get to know about the other domains also. When we try to see the contrast between the classical and the quantum regimes, classical state is always a deterministic state, and quantum states are exist in a superposition of states in which states are having different states are having some probability, and measuring the system will states. This can be further understand when we actually see the talk will be having an introduction to qubits and gates and speciality of these to be a unitary gate and understanding of the poly gates in the terms of I, X, Y, and Z gates and the Hadamard gate. I am sure all the participants are already aware of all these, but a little bit overview will help in understanding the working on IBM Composer, or it may be like a recap or a reconsolidation. And when we talk about the two qubit gates, we will be talking about formulations and then working with the lead to further advanced sequence. So we all know about the classical bit, which is endowed with a definite state of 0 and 1, where we talk the 0 to be the low voltage and high to be the high voltage. And analog electronic is something which basically has matured with this kind of formulation. When we are talking about a qubit, which is a quantum bit, which is which can be realized in terms of many types of which can be superconducting, trapped ions, neutral atoms, electrons. There can be a range of physical realization of these when we are talking about the physical systems. And in that, a quantum bit, it can be illustrated as, or can be taken an analog as a superposition of state 0 and 1. If I say state 0 to be a tail and a state 1 to be a head, it can be regarded, it is like a two-level quantum mechanical system and unit of information used in quantum computing. So what do we actually, how can we visualize superposition can be seen here in air. It has got no bound, or wheresoever there is a stable which is either 0 or 1. And when it is in the superposition of a state, then it is going to be the alpha. Mathematically, it can be written as alpha times the state 0 plus beta times state 1. And state 0, we are saying it as a tail, and state 1 as 1. And when we say that the mathematical formulation and the laws of physics are ruling this, we say that the probability of the coin landing in tail is mod alpha square, and probability of coin lending in talking, and in the terms of Dirac notes elucidated further. And it is also linked with the normalization condition, which says that the probability square mod alpha square plus mod beta square is equal to 1. That is one of the important condition which says that the coin must land either in head or a tail, so the sum of probabilities must be equal to 1. Let us further see deep dive into this, which says that in the case the coin is going to be an unbiased coin, what do we mean by alpha and beta? So in that case, if I say that the probability, or I may say that alpha mod alpha set this value with a simple mathematics that alpha and beta is 1 by root 2. And if we have got this, the case of an unbiased coin, what will happen if my coin is biased? In that case, how the normalization condition is met can be seen further like this. Suppose I have an equation that is under root 2 by 5, the state 0, plus under root 3 by 5, the state 1, which is equal to my superposition state. So what is the probability of a head, and do these values satisfy the normalization? condition. So I would like everyone to kindly utilize the head in this particular case and normalize the condition. On this,
Yes, screen is visible. Only in between your screen getting pause.
okay,
Maybe
that may
maybe
be the
maybe because of internet problem.
That's right. That's right. So in the chat, I would like to see that I have a question to ask to be answered. What is the probability of a head in this particular case when the when it is a case of a biased coin? And do we have some answers in the chat? Gagandeep has written 9/16. Some more answer. Probability of a head is 3/5 by Sahib. Can we have some more answer? Is the normalization condition being met? No worries, it's being met. We have more answers. Sahib is writing, yes, these is satisfying the normalization condition. Anirbit has written that it is 2/5. Bandhana has written 2/5. So let us see that what do we have in store for us further. So we can say that spinning coin, and how would I know that a spinning coin will have is a basically biased or unbiased? How can I check if a coin is biased or not? So if heads and tails, I can then get, and in that case, it may happen that the probability is same, and then we will call it as a biased case. Okay, so in the direct notation, if we say, we can write it in terms of computational basis states as alpha times state 0 plus beta times state 1. And that is my wave function psi. That is the case in terms of direct notation. And here, if I write the state 0, it can be written in the vector or a matrix notation as 1, 0, and beta. So it is convenient to write in understanding the gates, which are a combination of different matrix elements, and we will see those one by one in the forthcoming slides. So probability of measuring psi in state 0 is mod alpha square, and probability of measuring psi in state 1 is mod beta square. So why gate-based implementations are important? Gate-based quantum computers use quantum gates to transform our initial quantum states. These quantum gates can be represented by unitary metrics, and experimentally these gates can be applied physically using mirrors and beam splitters and a long claim that if a unitary operation is having on this psi, and that is equal to psi prime, then according to the mathematic or linear algebra, u dagger is equal to u dagger u is equal to I, where I is the identity matrix. And u dagger is nothing but the complex conjugate transpose of a unitary matrix. And all these mathematics also leads to give us that U inverse is equal to U dagger. Let us see why this all is important. Why do we have importance of unitary matrix when we are talking about gates, and what all this lead to. I will also encourage participants, especially to also utilize these Python and Scilab or any other language in more girth. So let us see in Scilab, I can just demo that I can just show that how these all can be written and how one can check different mathematical operations and their utility. Here you can define state 0 to be 1, 0 and state 1 is equal to 0, 1. So I can utilize my pen in order to explain it further. In case somebody is interested, I can then further elaborate it later also. So here state 1 would mean we had written state Z is state 0 as a matrix element 1, 0 and state 1. This is how we define this in a learn semicolon 0. So that is 1 is the first say element of this row and 0 is the second row. So this is how elements are entered, and another one is 0, 1 which is state 1. That is a ket in state 1. We can take by writing this just prime, we can take the conjugate and then we can define z as 1 by square root of 2 state 0 plus 1 of square root 2 of state 1, and then we can also define a quantum state with a complex number also, and when you take its this complex conjugate, then you just take this a prime and then you take the inner product of a state written as 0, and then if you just try to write want to show it, then in that case the state 1 conjugate star state 1 is what is showing here, and one can implement this using any programming language. This way one can also have a utility of aligning all these understanding with the help of programming languages also. So is my voice breaking?
Yes, your voice is breaking. Maybe you can try to switch, turn off your video. Maybe then the bandwidth maybe improve.
Yeah, that will be, I think, yeah, that will be really useful. I know that. Maybe it is better turn off their videos so that we can have a better bandwidth.
Yep. Okay, please continue.
Okay, just stop it. I'm not able to replace this bar here. Okay, let me again go to the slide mode.
Yes.
Okay, fine. Is it better now?
Yeah.
Okay, so in this case, one can see when these are orthogonal to each other, then this product is going to be 0. Otherwise, when they are in the same state, then this product is going to be 1. So all this can be implemented using Scilab and Python also in order to have a better understanding or in-depth understanding of these things which are happening. So when I have this unitary matrix U, which is I suppose is a identity. So we can confirm whether these take a complex conjugate, and first you take a transpose and then the complex conjugate of this, and then try to see whether U dagger is coming out to be equal to U inverse or not. One can get to know whether it is a unitary matrix or not. So please note it down. You can try at your leisure time that whether these two matrices are unitary or not in nature. You can first do mathematically by hands, and then you can also try to use it using a programming language also. So let us now see that in the we can also define matrices in different programming languages. Like if I have a matrix of say 2 cross 2, say elements, in that case I can write it as 0, 1, syntax of different programs. Going to quantum, IBM Quantum Composer, we try to understand its basics in the form that how qubits are initialized in different states. So these are initialized in 0 state, that is a default value. Gates can be implemented on different states. It can show probabilities, that is the percentage of the computational basis states, and it can show amplitudes of the computational basis states, and it can show the state and the phase angle on the surface of a sphere. So if we try to see this on a block sphere or a Q sphere, there is a difference between these two. So one can get to know that single qubit states that are not entangled and lack global phase sphere. And again, one needs to because we need to know the complex variable knowledge in order to understand that how these are represented in terms of the bit value and the phase value. And in this case, it can be written as cos theta by 2 state 0 plus e to the power I phi sine theta by 2 state 1. So one can see here the r value, theta value, and the phi value. And when we express it in the terms of spherical polar coordinates, we can always see that the state 0 is a default state, and then if it is changed by an angle of one say 80 degree, then it is the state 1. And this all is available on wikipedia.org or any other book is also available in order to want to what are gates are basically some of these are poly gates, which are I, that is the identity, X, Y, and Z gates, and there is a Hadamard gate which is represented by H. And when we go further and try to correlate that, we saw the matrix representation and tried to see whether that matrix representation is going to be unitary or not in order to qualify to be a gate. And if I'm talking about here a poly X gate, it is represented by 0, 1, 1, 0. And what it does, what properties it has got, and how to show that it has got this kind of a property. It says that it converts a 0 state to some other state and a 1 state to some other state. So can someone X is operating on state 0, what will be this question mark? That is the first question I am asking, and please answer in the chat that what will be the outcome when a Pauli X gate is acting on a 0 state. So please utilize chat for writing the answer. Diljit has written, Bandana has written, Agrim Bhatt has written state 1, Srinath is writing state 1. Very well done. Okay. Can we prove? How can we prove? Can somebody unmute and tell that state 1, if we are going operating, unmute and tell me? Can we show mathematically?
Ma'am, using the outer product form of the operator.
Okay, so in that case, can I show it like this? That if my X, just a moment, let me switch on my pen. Or I have it on my next slide. I can show it here. You can write this as a poly X gate working on 1, 0. And if you do the matrix multiplication, you will get 0, 1, which is state 1. And similar way, if you take this ZX gate working on state 1, you will get state 0. Is this point clear to everyone, or consolidation of what you must have done earlier? Is that fine? So at this stage, we take a pause and we try to see a quiz, and that quiz is going to be online. I would request everyone to kindly join the quiz online by the following link, which I am sharing just now. Just a moment. Sorry, something went wrong. Is my screen visible again?
Yes, visible.
Okay. Go to slido.com. So say try to utilize this QR code here. Is my screen visible again?
Yes, visible.
Okay. So please join at this slido.com with the code 199. If some of you are not able to join, that is fine, but I would appreciate if some of you are able to join the quiz. This is based on what all you have done earlier and what we had a recap also today. See the screen. Optimus has joined. Is my screen visible with those who are joining in?
Yes, we can see.
Okay.
I can also join.
Okay, that's right. Please, others do join. It will be very simple just to reconsolidate before we move further. I will appreciate if most of you can join in. 10 people have joined, 10 participants have joined. Some more, please do join in. 12 now. We can wait for 1 minute. Good, very nice. Requested to join, please. Very nice. If anyone is facing any technical issue in joining, can also mention it in the chat. So we will not wait for that participant, but rest are being given time to join in. 21 we have right now. Sugamji, should we wait for some more time or should I start?
I think you can start.
Okay. So it has got a timer. Within that timer, it will be showing a bar. So please try to answer within that timer. Otherwise, it will switch on to the next question. So that is why it is important as quickly as possible. Manas is saying that he's having some technical issues. So no worries. You can just view in case you are not able to join in. It is fine. Okay. So let us begin it. So it says that if an X gate is applied to 0 state, what will be the result? Please choose your answer. Timer is also shown to everyone. Time is up. Okay. So everyone seems to have answered very nicely in this. We have got 95% responses as a correct response. Next is, how is a qubit different from a classical bit? Multiple states simultaneously, qubits can only of uncertainty. Still, everyone can join in. In case you are not able to join for first two questions, still it can be joined at any point of time also. So those who have not been able to join can keep on trying also, so that they don't miss it. So the majority is saying qubits can be in multiple states simultaneously, which is a correct answer. And the next one is, consider the following state. What is the probability that my state will collapse to a zero state upon measurement, where psi is equal to 1 by 2 zero state plus square root of 3 by 2 one state? So 1 by 4 are saying which is a correct answer. Next is, what is the primary type of qubits used in IBM's quantum computer? Let us see the answer, which is superconducting. 53 participants have written correct, and rest can check the answer. In what state the qubit in IBM computer is initialized? Majority have given the correct answer, but some have written a wrong answer also. No worries. Which of the following gates form a set of poly gates? Here, majority answer doesn't seem to be correct, so no worries. The Hadamard gate is important because it negates the states. It can create superposition of states from the individual states. It is not a Pauli gate. It is in a complex state. What is the dimension of matrix that represents a C0 gate? This is our question number A. So majority has a correct answer, 4 cross 4. And this is question number 9. On the IBM Composer, we saw two histograms, and these are called probabilities and state vector, probabilities and phase, probabilities and amplitude, probabilities and Q phase. This seems to be distributed answer, and the correct answer is probabilities and state vectors. In case, we will have a look on this in the forthcoming slides also, so this can be reviewed upon. Does the following state satisfy the normalization condition where we have got psi is equal to 1 by 2 state 0 plus half state 1? We have the scoreboard here. Many have got say 8 out of 10, with Dr. Sugam leading with the timing of say 1.51, whereas rest also have got 3 more have got 8, and but the timings one can see is increasing, and Shalini has got 7 out of 10, but her timing is she is very fast in say getting these responses by say, and we will see that how we can address to that. So congratulations to everyone for participating, and I hope this way was also a learning in a different manner, so that we can try to build upon, or we can try to inspect what are the things which we need to reconsolidate on, what are the things which we are very sure of, which we can answer in a very say short period of time. So now I move on to my slides again, and we'll try to show that what all these poly X, Y, and Z gate are doing. What do we mean by Hadamard gate? And when we check it on the IBM Composer, then how can we verify? How can we verify unless or until there we don't know the theoretical say framework of that, we don't know how do they mathematically represent, we will not be able to check our answers on the IBM computer or composer, or also on the Qiskit. So it is required that the mathematics and the other theoretical background is very sound when we are going to talk about. Could be any, because these days many simulators, composers, programming languages are being used in order to see the manifestation of these gates or implementation of these gates. So here it is very important to understand these theoretically also, and also visually also. So I am going to show all these in the forthcoming slides. Thank you so much for your participation. So moving further on, is my screen now showing the Pauli gates?
Yes, it's showing the polygates. Yes.
Okay. So we can say that poly X gate is analogous to the NOT gate in classical computing, and its action is to flip the state of the qubit. And we just saw mathematically also that a 0 state is being converted to a 1 state and vice versa. And I can now move on to the IBM composer in order to demonstrate that the hardest question, see that how do these look like. Not repeat that. I can just open it from this one. Is my IBM Composer clear, visible to everyone? Please write in the chat if you are seeing it for the first time, or those who know it can write yes on it, so that I get to know that how much deep I need to go in order to do this. So can you just write if you are using it? In case you are using it, where are you? Are you at the intermediate level, or you are at the basic level, or what is your, some of you are writing it as a first time, so no worries. Okay, fine, first time, it's okay. Never seen it? Okay. So in case you are using it for the first time, you can get, you need to sign it up for it by making, using your email ID. And I have already done all those things. So it looks like this. It is called IBM Composer. And here, these gates are given to you in a very, very user-friendly manner, that you can always delete a gate, you can always add a gate, and you can work on different qubits here, and you can see the that is why I think one answer was not done by majority of you, because this is you need to know that what does it show when you are working on Composer. It shows probabilities, it shows state vector, it shows Q sphere. When you are dealing with different types of different types of qubits, then you can measure the state and you can also get the phase angle here. And also interpretation is there for each and every operation you do. Can you see here A0? Can you see it here, A0? Is it visible?
Yes, visible.
Okay. And then I can choose this gate, which I can pull it and I can work on this qubit. Prior to that, I would like to show that was my question also. In what state the IBM. So state 0 is, and here on right hand side, if you see, it is showing an arrow, which is showing a state 0 with a probability 1, and the phase angle in this case is 0. So phase angle is shown by these colors. If this color is blue, then it is 0 phase. If this color is magenta, then it is phase is pi by 2. If it is red, then it is pi. And if it is other greenish color or yellowish color, then it is 3 pi by 2. Is this clear to everyone? Is this, I have expanded it?
Yes,
Anyone?
it's visible.
Okay. So I go back. So this is the initial probability of state 0 and state vector, which is seen here. And this is my that way which we try to understand that how does it shows different states and phase angle. If I click on this phase angle, it will show me in the writing form also, but I can deactivate it. It is up to me to see what I want to see. And now on this uh, first qubit, I try to a poly. Which gate is this? Can somebody tell me? We were doing the first gate, no? What was that? Pauli? Please write in the chat. We were doing this gate. Pauli, X gate. Is that right? Yes, right. Right. Some of you have written right. Okay, so I go to my composer again. So can you see that it has, after applying this, it has changed the state 0 to 1 state? Is it seen? Can it be appreciated? What it has done? Earlier state was 0 state. Now it is 1 state.
Yes.
I have applied poly X gate to this. Is that clear?
Yes, ma'am.
If I apply 2 of these, what will happen? Can somebody tell me? Can write in the chat before I apply? If I apply another X gate, poly X gate, then what will be my output? I will get back to my. Very nice. I am getting responses. So we will get the state back. Is that clear to everyone? Is it fine?
Yes, ma'am.
Okay. And you can identify different gates here. It is T gate here. It is Z gate, Y gate. And we will also be talking about this gate, which is called C0 gate, which will be applicable on 2 qubits. And all these can be implemented using the quantum composer. So I go back to my slides. Any doubts here? Then I can get back to you later also. Let me first finish my slides so that at least we have some substantial knowledge. I have made those things in say in the slide form also here state 0, and this it is initialized in state 0, and then we have got this is a visual representation of the poly X gate, so it is rotating about the x-axis. So can you see that? And this I have taken from our website. I can share the link if anyone else is interested. It is luisagitbook.io, in which you can find these simulations. So what does it say? That if you are applying this to a 0 state, it is getting converted to 1, and 1 state is converted to 0. This is causing a rotation about x-axis, and if I apply this in the composer, we just saw that I go back to state 1, and here you can see that the amplitude is now, this is now in state 1, and angle remains the same. So this is how Quantum Composer, IBM Composer can be utilized for the visualization of different gates in this manner. Same way, we also tried that if I apply it 2 times, I will get back to my original state. So all I think is clear until now. Similar way, we have got Z gate. If my Z gate is 1, 0, 0, minus 1 is my matrix representation for the Z gate, can somebody work mathematically that what will be the answer for converting, how will it convert a 0 state? What will be the outcome to the 0 state and the 1 state after you have applied the Z gate on the 0 and the 1 state? Can someone tell me? Srinath, you have written yes. Have you written yes to this question? Same get as input. Okay, let us see. So if it is working on a state, this is a state 0. In that, it is giving me the state 0 itself. But when it works on a state 1, then it is converted to state 0 minus 1. So this is how a poly Z gate works. So what it is doing? It is basically changing, the 0 state remains unchanged, and the 1 state goes to minus 1. So one can see that this is a rotation about the z-axis. That is why the name is the Z gate. So one can have a X, Y, and Z directions in this case, and then one can see that how these rotations are being rendered in order to have a better understanding of these gates. Similar way, how I can sum up the poly Z gate? Its action is to flip the phase of state 1 and leaving the state zeros as unchanged. This is what a poly Z gate is doing. Same way, we can always implement it in the IBM Composer, and then we can try to see that how does it look like. And so instead of now X gate, I will be calling a Z gate, which is working on state 0, and it will render the state 0 as it is. But when I've applied first say X gate followed by a Z gate, so what will this X gate do? It will change the 0 state to 1 state, and after, if you are applying the Z gate, it will change the phase of this by 180 will be the change in phase of this, which will be negative. So in this case, this is how mathematics helps a lot in understanding of these gates, as well as the visualization. You can write code in different programming language in order to understand their operation, and followed by you can always implement it in Composer, simulators, and many other places. So moving further on, is it clear up till now? Can you just write in your chat? In case there is any doubt, I can try to clarify that. Please do write in chat. Is it clear until now? If anyone has any doubt, it can be cleared. Otherwise, I can move further. Thanks for your response in the chat. So with that, I move further. Now is the Y gate. In this case, the matrix representation for the Y poly Y gate is 0 minus iota, iota 0, and it is working on state 0. So you can see it is 0 I, and other case it is minus I 0. Let us see how we can write it. So what it is doing is that it is converting a state 0 to state 1 with a iota, and a state 1 to state 0 with a minus iota. And in this case, this shows the rotation along the y-axis, and this is what it is doing by applying it on the. So what it is doing, poly Y gate is known as a bit and a phase flip gate. Its action is to flip the state of the qubit and change its phase also. And one can always see, in order to get the additional I phase, one can utilize a combination of X and Z gate. And after this, you can again implement it using the composer and try to see, which will give you a much, much better understanding of how these actually work in different domain. Next is the Hadamard gate, which is again a very important gate because it is useful for converting basically converting a 0 or a 1 state into a superposition state. And a Hadamard gate can be given as 1 by root 2, a 1 1 and 1 minus 1, and you can again try to work on, in order to understand it very well, you can again try to see that how matrix operation can be done on state 0 and state 1 in order to get the outcome, which you are combination, which is along say X and Z direction. It can be a combination of X and Z direction, and one can see how much is the angle in this particular case. And this is the visualization of, one can see that it is a rotation, a combined rotation of X and Z, and there are many other ways in which it can be implemented. So here one can see that if this 1 by root 2 and Hadamard gate is represented by 1, 1, 1 minus 1, it is working on state 0. So you will get 1 by root 2, 1, 1. And if it will work on state 1, you will get 1 by root 2, 1 minus 1. So in this regard, you will have a superposition state of say both the states, and in that case one can always see that this application is giving rise to both 0 state and 1 state with some probabilities and some say amplitudes, and this is what is it is doing, which is a very, very important thing required in order when we work with different qubits. And here on simulator, again, you can implement it. Different combinations can be implemented. And so I think with this much of exposure, you should be able to utilize all these. And because I want to also touch upon the Qiskit, which is in which you can do programming using Python, and then you can try to basically visualize as well as obtain these gates. And then you can work on these as a standalone way of working also. So when we are talking about C-NOT gate, is there anyone who has written something? Okay, fine. So if I talk about C-NOT gate, which is a controlled NOT gate, which is given by CX, it is a combination of a 4x4 matrix, which all of you answered very well in the quiz also. So if we will be dealing with 2 qubit gates, then when the control in 0 state, so this one is the control. These are the 2 qubits. So if the control is in 0 state, it does nothing. And if the control is in 1 state, it applies a poly X gate on the target. So is this point clear, that how does it work? And one can check it mathematically also and try to see that this is the summary of a controlled NOT gate or CX gate. What it does is, if the control is in 0 state, it does nothing. And if the control is in state 1, then it applies a poly X gate on the target. Is that clear to everyone? So moving further on. Okay, so this is my say, and when we are talking about say 2 qubits, Now, combinational, this can be represented in computational basis states as 0, 0, 0, 1, 1, 0, 1, 1. So one needs to understand that how do you get, what do we mean by 0, 0 state when you are having 2 qubits? So I think by now you all must be knowing that, but I am assuming that, otherwise if it's required to be elaborate, I can do that. But right now we are assuming that this is in a state 0, 0. And when you apply a NOT gate, it is not doing anything to this. In case you are just applying a NOT gate, when the 0th 1 qubit is in 0 state, it does nothing to the second qubit. Whereas if I try to see the implementation of the second condition, then I am changing the first qubit state by applying a X gate. So now the first qubit is in state 1. And then when I applied this C naught gate, then my state vector is going to be can be represented in this manner. So one can see that here it is 1 0 state, and when this is showing the 1 1 state, which is the, so this is how a C naught gate works. And now I have, after demonstration on the IBM Composer, let us try to understand introduction to Qiskit using Python. How many of you are aware, are basically knowing Python? Can you just write in the chat so that I know the background, that how many, and accordingly I can tailor make my session. Can you just write how many are knowing Python? Or how many do not know Python? That will be better way of asking. I assume majority of you know. Sarita doesn't know. Sahib Helder knows. Okay. Not much. Okay. So very many also do not. Okay, fine. It's okay. So here, whatsoever we did on a IBM Composer, at the back end, one can utilize programming in Python, and there is a very popular package which is basically released by IBM, which is called Qiskit. So here we will import the relevant libraries. That is Qiskit. There has been a very, very recent change in the Qiskit. Now, from 1st July 2025, the previous version will no longer be working on that, and the new has been released, and there are many, many changes in that. So I will try to highlight those changes which have occurred in this new version. So we will create a quantum register, which is a collection of qubits. We will create a quantum circuit like the one which we have made using a composer. These can be done using Qiskit also, but we will have to write the code for that. And then we apply the measurement gates. Then we transpile the circuit, and there are different possibilities of running it on different noiseless simulator, simulated noisy device, on a real device. And then we can plot the histogram of results. So these are the basic steps which are done in order to basically build a circuit in Qiskit by coding, and then you seeing the response of that on different simulator as well as real devices. So let us move further on. This is our latest version, as I have just said, which says that welcome to the upgraded IBM Quantum platform. This open plan is free, but it allows 10 minutes of access to quantum computer per 28 days. So it means that in 28 days, you can utilize these for 10 minutes for running the code. When you run the code, it will take that time into consideration, but it takes very less time. So one has to be very judicious in utilizing it for different applications. Again, you have to have count in this, and there are some running protocol also has been changed in this. Some API have also been changed, which I will be just telling. And then access utility scale quantum processing units, which is called QPUs. I think all of you know about CPUs, GPUs, but here when we are talking about by IBM different processing units, these are quantum processing units. So this is the front page which I have taken from IBM website. All of you can always see this. Then we install and set up different libraries. So these are the commands which can be utilized to call these libraries, and there is no one way of doing it. It can be done in number of ways. So in this case, pip install Qiskit and visualization. So all the things which will be drawn will also be utilizing some libraries. So it can be by using some other libraries also, but if you write within the square bracket visualization, then also it can utilize those libraries. Pip install Qiskit IBM runtime, pip install Qiskit AER. And then one has to set up an API token, which has again changed recently, an instance in IBM Quantum platform. Instances are basically virtual servers which manage the execution of quantum programs. And from Qiskit, then we will import Qiskit underscore IBM underscore runtime and Qiskit runtime server service. And in that particular token and instance will be matched up with that particular device on which we are working. So with this, we will be writing our code. So we will write from Qiskit import, we will be requiring quantum register and quantum circuit. And here Q1 is quantum register 1, which we are labeling as Q1, and Q2 is quantum register 1, and we are labeling it as Q2. And then we build a circuit. We name the circuit as quantum circuit Q1 comma Q2, and then circuit.cx Q1 comma Q2. So it means that we are applying a NOT gate to Q1, 2 qubits, Q1 and Q2. So this is the code for that. And then circuit.measure all. So these are the two scopes which are used to basically measure the different states which are there in which and this is basically for visualization. One can see that, and then we use a command circuit.draw output is equal to MPL. It utilizes the matplotlib libraries in order to draw this. One can see, can one see the difference between the first circuit and the second circuit? What is the difference? What is the difference between the first and the second circuit? Someone can unmute and tell, or can write in the chat. I can read the chat. An extra additional X gate before the C naught gate. So if I want to make, say, this circuit, just a moment. I think I have gone to the next slide. Just a moment. Can you see that in order to, what is the difference between this and this circuit is an additional X gate, as has been rightly pointed out by some of you. So I will, in order to make this circuit, I will have to insert another command, circuit.x Q1 before the C naught gate. So it means that on the first qubit Q1, we are applying a X gate. And after that, we will write the rest of the code. This is how you build on circuit by writing a code in Qiskit. Is this point clear to everyone? Can you just write, indicate in,
So
because this is very important.
Yeah, hello.
To
So, yeah, this X command has to be
understand.
inserted before circuit making, no?
Yes,
Okay.
please tell.
No, before circuit making, we have to insert the command, no?
Before the C naught gate, before the C naught gate. Here I have applied C naught gate to both Q1 and Q2. That is after so I will be first inserting circuit.x Q1 before the C naught gate command, and that is this command.
Okay. Yeah.
Circuit.cx at Q1 and Q2. Is it clear?
Yeah, right.
Okay, fine. So can someone please, all of you can write that, is this point clear? Because This is very important to understand that we are applying a X gate first to a qubit Q1, and then we are applying a C0 gate to both the qubits. So I here the syntax change will be that so Gagandeep is writing, so wherever you need any operation, you must insert a circuit command with that. That is right. We have understood it very well. And this is just a sampler example, just to tell you that how does it work. It is not possible to actually include everything. So that is why I have highlighted by making one circuit and then by writing a code for the one circuit. And this is additionally written in order to tell that if we want to apply on Q1 X gate, then that will come first, and then I will be applying, say, no, C0 gate on Q1 and Q2. So there will be change in the basically code, and consequently the output will also change. I hope this point I have been able to clarify to all of you. Can you just if you could write in the chat, it will be easy for me to go on to the next slide.
Ma'am, what about initialization? Have you taken care of it by in default?
That can be that another command can always be added, but in this case, in the default value, we don't require it. When you are going from one circuit to another, then it is of the most important thing. Okay, that can always be done without any problem. So here there are say different gates here. Commands for different gates I have written here. So if I want to apply the poly identity gate, then it is circuit.id and I'm applying on this Q1. If it is circuit.x on Q1, so this is for application of the poly gates. This is for the application of rotation, single qubit rotations can you see in this case, the argument will be theta and Q1. So it will depend by how much angle you are wanting this rotation. So it will have two attributes as input, and Hadamard gate is circuit.h and it is Q1, and circuit.cx Q1 comma Q2. This we have utilized in the given example. So now I talk about the local simulators which are available with IBM. Again, as I told, these are the very, very recent changes, and after 1st July, these changes are going to be in use rather than the previous ones. So, and these are much more advanced, basically simulators as compared to the previous ones, and they have got different meanings. So this again I have taken from the IBM website. All of you can have a look on there in order to understand this further. So there are three kinds of simulators which we can talk about. One is fake backends, another one is AER simulator, and the Clifford simulation. Whatsoever Composer is implementing, all those are in the noiseless basically simulator. So Clifford simulation is basically a noise-free simulation. It is suitable for very large circuits, hundreds of qubits if you have. It is extremely fast and suitable for stabilizer circuits and large stabilizer circuits and error correction. But real life is not noise free. All the qubits which are being basically processed or fabricated, when there are interaction of qubits with one another, or otherwise also there are lots of noise. So the real device is actually having noises. That is why it is a challenge to make error free or fault tolerant basically quantum computers, be it any kind of qubit. We here in the IBM, we are talking about the superconducting qubits, but there is work going on. Dr. Sugam is also working on these ion trapped version in which electrons are being used, and there are many people are using other kinds of qubits also. So here, when these are in the real devices, there is a lot of noise which comes from the say environment. There are issues like decoherence happen. It means that they lose their existing state. All these issues are there, which are hindrances and are being channelized and are being addressed by different scientific communities and engineers as well as companies. So in the AER simulator, it can be custom or based on the real say QPU calibration data. It can also handle larger circuits and shorter runtime for a wide range of simulations. And the third one is fake backends, which mimic specific IBM QPUs by using snapshots. And it has got limited capabilities of it is limited to the capabilities of mimicked QPU, and it has a moderate runtime for QPU specific test. So, and there is one more, say, step in between, which is called transpiling. And that transpiling is something which I will be describing in the next slide. So here again, this is a description of the simulator. So noiseless simulator backend, we will write a command backend is equal to AER simulator, method is equal to stabilizer. Noisy simulator using fake backend. So here backend is the fake Brisbane, which is available with the IBM. And in order to retrieve latest backend data, backend refresh service is used. And noisy simulator using AER simulator. Then we will write real backend is equal to service.backend IBM Brisbane. You can see in going from this to this, there is basically a different kind of, say, simulator which is available with IBM, and backend is equal to AER simulator dot from underscore backend real underscore backend. And real device would mean that which is having a lot of noise, and that is also available from IBM Brisbane. So depending upon which kind of simulator or real device we are interested to get data, depending upon that, we will write the code. And there is another step which is called transpiling. What do we mean by that? Also, I will explain. Transpiling is or transpilation is what makes the input circuit compatible with the basis gate set and topology of the actual quantum device. It can also optimize the circuit to reduce the effect of noise. And there is a command which is called, or there is a function which is generate underscore preset underscore pass underscore manage, which can define the level of optimization required to transpile the circuit. So what do we mean by transpilation is that, suppose there are we are trying to make any output circuit which has got a different sorts of gates. Those gates may not be available as the base standard gates with that particular simulator. So what it will do, it will try to convert that required gates into the standard gates, and optimization is also required in that. And if I want no optimization, I will here write optimization underscore level is equal to 0. If I want a light optimization, then I will write it as 1. If I want a heavy optimization, then it is written 2. And even heavier optimization can be done, then I will write here 3. And more the optimization, more longer is the transpilation time, more longer will be your time run of that particular program which you are writing. So all these are the intricacies which are there when you are working with basically Qiskit. Now these are the results. Suppose I have taken this circuit, which is a very, very simple circuit. I am applying a CNOT gate. And when I work on a noiseless simulator, and I have taken here 1000 shots. So in case there is a noiseless simulator, you can see that all the states are in the same state and there is no error in this particular case. But this is not the required condition in the real devices or in the simulated device. In simulated device, we can add noise according to our requirement, or it takes care of the introduced noise according to the to our requirement. So in that case, you can see that instead of all being in the 0, 0 state, there are other state, there are errors. It means that there are measurements available in the other states also, which is not correct. And in the real device also, if we use the simulator, in that case also one can see that instead of having all in the state 0, 0, there are availability in the other state also. So people are writing codes in order to take care of these errors. They are trying to write algorithms. That is what is another domain of quantum computing, that is called error mitigation or fault tolerant quantum computers. So in this particular case, I can say that we had in this session an overview of qubits, what qubits are, and their utilization their utilization in conjunction with quantum gates and quantum. So how do we build quantum circuits working with the IBM Composer, and demonstrations using Qiskit. And Qiskit actually requires a little bit more involved knowledge of say Python also, and I hope that this may motivate some of you to actually work in this field, which is a very upcoming field. And there are many universities and many engineering colleges and many institutes of repute in India are working on these, and they are developing different types of qubits, different domains of it is being basically addressed. In National Quantum Mission, a lot of money has been assigned for these upcoming this field, which is a very challenging as well as exciting field. So all of you are requested to take part in these initiatives. So with that, I can thank the organizers for giving me with this opportunity. Thank you, Dr. Sugam, and thank you, the Atomic and Molecular Society of India. And these are the references which I have utilized. Mainly, these are from IBM. And so this is IBM Quantum Composer, and also Qiskit, and Quantum Computation and Quantum Communication. Nielsen and Chuang is a book which can be utilized by the students. So with that, I thank you everyone for your patient listening. Thank you everyone.
Okay, thank you, ma'am.
Thanks a lot.
So it was really wonderful. And first of all, I would sincerely thank you for accepting our request to teach all the students and teacher who are actually um, uh, joined us on this ISAMP workshop. And what you have taught, particularly on the IBM Composer and Qiskit, to all these ISAMP participant was wonderful. Your
Thank you
session,
so much.
I mean, so
Thanks.
it was very informative, actually, I can say, and very engaging as well. I think for the 1.5 hour, everybody was completely engaged. No one get any time to get divert anywhere. You explain this quantum gates using this IBM Composer in a such a clear and visual way. I think I can say it might have definitely helped every student to understand how these gates changes states, okay, and how can you see on this blogosphere how they are moving, and it give a very clear visual teaching that now uh, which creates a more I can say clear understanding for these for these states. And of course, this visual approach always may make this complex topic much more accessible. So in that way, I think your approach is very good, very nice. I liked personally very much.
Thank you so
And
much. Thanks a lot.
and particularly this Qiskit programming, you explained, introduced everything with very clarity. And I hope that all the students might have got the very strong and solid foundations to start exploring the quantum coding. And I hope that everybody will like to do it. And definitely the one thing I liked much is your online quiz. And it was really very informative and added a lot of fun in interacting with all the elements you added there. And I hope everybody enjoyed that session. So again, I truly appreciate your effort and
Thank you
enthusiasm
so much.
you put in your teaching. Actually, you are, I can say, you are a wonderful teacher.
Thank you so much. Am I audible? It is my delight to be a part of this. Thank you for providing me with this opportunity, because it is such a exciting field, and it is upcoming field. I am also a learner in this, and I think through this I have also learned that what are the things which are needs to be say emphasized upon, what could be the way in which it can be make more and more, I think, visualized to the students. This is what I believe, that visualization always add to
Exactly.
understanding, better understanding. So thank you so much for providing me with this opportunity. And thank you everyone for your patient participation in quiz also and patient listening also.
So anyone from the participant side, if they want to uh, uh, make any comment or any suggestions to make this kind of uh, online workshops more interactive in the future. Because this is our last class, and tomorrow you will be having your final test, and that will be at the same time from 6 to 7. That will be a 1 hour class, and that will include everything from the starting from the quantum mechanics introduction, and then with the quantum qubits, gates, then algorithms, and then 2 hardware we discussed, that is the superconducting qubits and ion trap, and also about today's class. So everything will be going to be included in the tomorrow's final test.
I will be happy to answer any question. Should there be any?
Madam, this is Anup.
Yes, Anu,
So,
please tell.
my question is, what is India now current in terms of status for having an hardware with a quantum computer? Like we know that IBM, Google, all of them have, but
Actually,
they are struggling with that scalability issue. So,
many
in India, what is the current status? Is there any developed one of quantum computation already, or is it in process?
Actually, in India, under the National Quantum Mission, there are 4 verticals. And those four verticals, one vertical is quantum computing, quantum communication, and also there is quantum sensing, and there are many other quantum materials. So different research institutes are working on this, and I think at IUAC also, ion trapped is underway and basically based on electrons. And there are I think many because this is only recently last year or last year, this was basically this call was thrown. All these are working, different institutes are working on this, and I think with the passage of time we will see more efficient and scalable quantum computers from India side as well. As I told, error mitigation, there are efforts to mitigate error. There are efforts to basically make it fault tolerant. That is, there are many partners or many collaborations in these. Many stakes are there. So I think it is going to be much and much clearer in forthcoming months that what is the current status and how these are all working on this.
Okay, thank you, madam.
Can I add, ma'am, some few lines here?
Yeah. Please do add. You must be having also a update on this. Please do add.
So, of course, there are many government institutes which are engaged in the creating such quantum computing platforms. And the leading one, of course, is the ISC Bangalore.
Mhm.
Along with that, there are some startups also has come up. And one of them is the now Iron. There is a Bangalore-based company. I'm forgetting the name of that company. There is something INQ or something like that. I think you can check. And they recently they are developing the superconducting qubits, and they have come up with a 25 qubits quantum computer. So that is I guess the latest and the biggest number of qubits somebody has proposed in India particularly, and that is the startup just started, I think 3 to 4 years ago only. And if we talk about government institutes, so in collaboration with the ISC Bangalore and TIFR Mumbai, their joint collaborations, and they are actually developing quantum computer, and they, I think, mentioned that they also have developed around 4 qubits platform. So these are the, I can say, say that latest development what we can see. And I can see in the chat box, somebody has asked that this 10 minutes in 28 days are very less. So how much they're going to charge? It's very costly now. So IBM quantum computers, I think they're going to charge you around 100 US dollar per
When
minutes.
I was running these circuits, this is the latest protocol, and in that use these are the prices, or these are the values which are given free of cost, but other would mean that running of a circuit very, very particular about how much to run it before your final version is made. So in order to do that, first you will do all the other kind of other kind of pre-test before running it finally on the computer. So you will use it very judiciously.
So we will suggest you that if you are not actually making some serious business using the IBM Quantum Composer, better to go with the free plan only, because the buying is definitely going to be cost a lot.
That's right. Any other question?
Yeah, I remember this company name now. It is called the QPI. Now, this is Bangalore-based company, and
Okay.
they have now come up with the 25 qubits quantum computer.
That's great.
Anybody else want to ask any other question?
Excuse me, sir.
Yes.
So I am a MSc first year student at HNB Gadwal University, Uttarakhand. So I want to ask you that because I'm passionately curious in this quantum computational field. So I want to ask you that in which subject I can do my specialization so that I can go further in this particular field. Either it will be high energy physics or electronics or laser.
In quantum mechanics?
But sir, in our college, there are only 4 subjects for available for the specialization. They are high energy, condense, laser, and um, astrophysics.
I mean, if you read your quantum mechanics in depth, it is more than enough.
Okay, sir.
I mean, all these 4 fields you have mentioned, I mean, they're not going to help a lot, okay, in this field. So better that study your quantum mechanics course in depth, and that is more than enough.
Okay, sir. Thank you so much.
Can I also add,
Yes, please.
in case you have the additional things like programming language, a solid mathematical or linear algebra, or these kind of things as a base, then afterwards you can switch to any field in this particular domain. And in condensed matter physics, if you are basically, there is work going on quantum materials also. So quantum
Yes.
materials is also a very upcoming field. So it will depend upon which vertical you would like to work on, but the basic foundational knowledge of physics and also of mathematics will all, and programming language will always be an asset which you can utilize in your later, say, applications.
Okay, ma'am. Thank you so much.
Regarding this question you're asking, this I will ask to from the ISAMP what are their criteria, and we will let you know tomorrow. Yes, anybody else having any other question? So tomorrow there will be a class. I mean, it's 1 hour class and then 1 hour quiz. Okay. So I will try to make a summary what we studied in the last 1 week, and that will be just for 1 hour. And then after that, you will go for the 1 hour final quiz.
Shugam sir, can I ask one question?
Yes.
Maybe you discussed, I have missed it, about one question I asked previously. So to apply Hadamard gate, we get the superposition state, and that can be physically realized by using a pi by 4, that wave pulse lecture. So what was
Pi,
this?
pi by 2.
Oh, yeah, sorry. So pi by 2. So that one, pi by 2 doesn't. And so what was the same physical realization we can do for C naught gate? So,
Yesterday I discussed no, in the when I told you that once we come to the
mhm,
platform, we will discuss how to implement the C naught gate. And
okay.
yesterday when I was discussing this iron iron trap, so I
Mhm.
discussed that how these 2 qubits, okay, can be how to make the pulses so that we can realize the C naught. So if I can again remind you, or maybe you can go and watch that lecture again. So try to take 2 qubits, let us say electrons, and initialize in the 0 state. So 0 state was spin, means spin up, and also the 0 vibrational levels. Okay, so you need a 2 states. So one is the spin, which is going to be act like a logical qubit, and then the motional state. Okay, so you have to initialize these 2 qubits in the ground state of the spin and the vibrational state. This is the first step. After that, you're going to shine, okay, on the first electron, okay, uh, blue sideband laser, a microwave in this case, but in the pi by 2 pulse. So when you're going to shine pi by 2 pulse microwave on the first electron, this is going to put, it is like a Hadamard gate actually. So you are applying Hadamard gate on the first electron. So this is going to put the first electron in the superposition state, correct? Are
Yes.
you getting? So it will put in the superposition state. And because you are putting this blue sideband, so you are applying a higher energy. So when the electron is in the, let us say, in the ground state, then second electron also will be in the ground state of the vibrational level. But if the first electron is in the higher state, okay, then the second electron is also going to be in the higher state of the vibrational level. So this you can see that the second electron spin always remain the down, but these 2 electrons will be both going to be in the 0 vibration levels or 1 vibration level. But one electron will be the going to flip the spin down, but other will always going to be up. This is the first step. And then the second step, then shine the again red sideband on the second electron. Okay. And that is going to implement the C naught gate. Okay. So if you go to my lecture again, okay, you will see this visual picture. Okay, how this pi pulse, okay, is controlling. Okay. So if electron is already in the 1 state, that is the control. So control is 1. Then only it is going to flip its spin. If it is already in the 0 state, it will not going to flip its spin. This is what the control gate is, the mom said, right? So when the control is 1, then only it is going to act like a poly X gate. So the second qubit going to change its spin. I mean, say going to flip the spin. So when the electron is already in the vibrational higher state and equal to 1, then only it is going to flip the spin. So it is acting like a control gate, control not gate.
Okay, sir. Thank you.
Okay. Anybody else before we close the session?
Yes, sir.
Yeah.
I asked to ma'am, like, what kind of work is currently going at Delhi University, in particularly quantum computing?
No, can you repeat your question?
Yes, ma'am. I was interested to know about what is currently done, what we are doing in Delhi University in the field of quantum computing.
And in Delhi University, I think some theoretical work is going on, as well as, but I am not very much updated on. But actually, because there are some new recruitment also, we have some specialized people who are working on different aspects of, and some people are a part of other, say, groups also. Because in National Quantum Mission, there are collaboration among institutes also. So I am not very much updated on this, but I can explore and get back to you. I know one name of Dr. Utkarsh Sharma, who is working on theoretical aspect of it. And Dr. Jyoti is a part of a group which is working on basically Iron Trapped One in collaboration with IUAC.
Okay, okay. Thank you, ma'am.
Does it answer your query?
Yes, ma'am. Actually, we got to know about Sugam sir's work in iron trap, so I was interested to know in what is going in Delhi University as well.
Okay, because I am in a college and here I am engaged in teaching, learning, and imparting that knowledge to our students so that they are aware of different aspects of it in order to utilize these composers and programming languages in conjunction with understanding the basics of it.
Okay, thank you so much, ma'am.
Welcome.
Okay, so I think if there are no further questions or any comment, then maybe then we can close the session here. And thank you, ma'am. Thank you
Thank you
again
so
very
much.
much
Yeah.
for such a
Thank
wonderful lecture today.
Thank you
And
so much. And I can be contacted by for if there is any query by any of the participants. I'll be happy to because they may try and then come up with some queries later on also. So those can be emailed to me. I will be happy to answer them. Thank you so much. Thanks a lot for the opportunity, and I take leave. Thanks a
okay,
lot.
thank you, ma'am.
Thank you to everyone. Goodbye.
So, okay, I think Jobin, shall we close this session?
Yeah,
Or
Sugam, I think we can close
yeah.
it. We have stopped the recording, no? Or no, not yet. You can stop the recording, no?
Let me stop.